An Atwood's machine consists of two masses, and they're right here, A and B, connected by a massless, non-stretchable rope and a massless, frictionless pulley. Mass A is 20 kilograms, mass B is 50. They are held at rest and then released. Draw a free body diagram and write the Newton's second law equation for mass A, then do the same for mass B. Find the acceleration of the two masses, and then find the tension, F sub t, in the rope. Mass A is lighter than mass B, so we expect it to accelerate upwards. So here's what's happening. You've got B is heavier than A, and you're holding them here so they don't move. You let go. B is going to pull down because it's heavier than A, and A is going to go up. So they're going to move like that. So what else do we want to say here? The acceleration is going to be the same. All right, the magnitude will be the same because the rope is not stretching and it has no mass. So as B accelerates downwards, A will accelerate upwards with the same magnitude. Tension will be the same for both masses because the rope is lightweight and the pulley is frictionless. We'll discuss that more in AP1 and also APC physics, but for now, just say the tension is the same for both. There are no x direction forces in this problem. Everything's up and down. So with all those words, let's look at mass A. We have tension, and you know what? Let me just go ahead and erase some of that stuff on Atwood here. Okay. We have a cord, or the rope, leaving A. So that tells you the direction of the tension force. It's in the up direction. Gravity, m sub a g, pulls it down. Note we're using a subscript here to distinguish mass A from mass B. We're saying that mass A accelerates in the up direction, so there we go. And then we go ahead and write Newton's second law. We have the sum of the forces on mass A is mass A times the acceleration. And what are our forces? Tension gets a positive value because it's up. Gravitational force gets a negative value because it's pointing down. And the acceleration is positive because that is also up. Now let's look at mass B. Mass B is accelerating downwards. It's heavier than A, so it's pulling A up as it goes down. We still have a tension force in the up direction, and we have gravity pulling it down. Notice how we drew the tension force a little smaller because we know it's moving down, so MBG has to be greater than the tension force. Our acceleration is in the down direction. So what's going to be the value, the sign on all these forces? Well, tension is up, that will be positive. M sub BG is down, that will be negative. And A will be down, it will be negative because it's down. Be sure to label each mass with the proper subscript. We don't want to confuse mass A and B. So we have the sum of forces on mass B will equal the mass B times its acceleration. Tension is up, it's positive. Gravity is down, it's negative, and acceleration is down, so it's negative. Then we just multiply through here, and we put the negative in front of the negative m sub b a. So we put our free body diagrams for A here and B here, and here's our Newton's second law, and here's Newton's second law for B. Now what do you notice we've done here? We've set both equations equal to tension. Okay, so over here we had tension minus m sub ag equals m sub a times a. We add m sub ag to both sides, and we come up with the tension force is m sub a times acceleration plus m sub a times gravity, the gravitational acceleration. Let's look at what we did for the forces on B. We got here on the last slide, and now the same as we did for A, we will add m sub bg to both sides, so that'll cancel out on the left side, and on the right side we'll now have m sub bg minus m sub ba. And I will take a second here to erase this and highlight the important parts, which the pair of arrows there is also pointing to. We have this equation for block A, notice all the, for mass A, and notice all the subscripts are A. And we have this equation for mass B. They're both equal to tension. We have simultaneous equations, two variables. They each two unknown variables. Each one has tension and acceleration. So two equations, two unknown variables, that's just fine. Since we solve both for tension, we will use the setting tension of each equation equal to each other method to solve equations. Probably could come up with a shorter name for that, but it tells you what we're doing. To make it a little clearer, we put our two equations here, one for mass A and one for mass B. We will set them equal to each other. That will eliminate tension as a variable. Now we will have one equation and one variable. You can now solve for A. So here it is. Here is, let's see, this piece here was A. That came from over here. And here's B. That goes here. And we know the values of M sub A, M sub B, and G. All we need to do is solve for A. Here's our equation from the previous side. What we want to do is get all the expressions with A, or acceleration, on the left side of our equal sign, and everybody with G on the right. So the first thing we're going to do is subtract M sub A G from both sides, and you're allowed to do that with simultaneous equations. So here this little bar tells you we're subtracting, as well as negative signs. So on the left, what happens? These two cancel, and we're left with M sub A. And on the right side, we now have M sub BG minus M sub BA, that's what we had originally, minus this M sub AG term that we subtracted. Okay, what's going to be our next step? We're going to add M sub BA to both sides. And why are we doing that? Well, hang on. Let me do a little erasing here again. Right there. Look at this term here. That has acceleration in it. We want it on the left side. So we will add plus M sub B times A to the right. So that'll get rid of it. And then whatever we do to the right side, we have to do to the left. So that you add those two equations. Here's what we have now. M sub A times A plus M sub B times A equals M sub B times G minus M sub A times G. Let's factor both sides. We'll factor out A on the left side, and then we'll get A times M sub A plus M sub B, parentheses. And on the right side, we factor out a G. So we have G, M sub B minus M sub A. Finally, we just divide, I kind of left that out, but we'll talk to it. We divide both sides by M sub A plus M sub B. And here's our final answer for the acceleration. Now we can substitute our numerical values into the equation. And we show again here, please wait until the very end to do this. That's the preferred way of doing physics problems. The equations are the cool things. The numbers can come later. And from a practical point of view, sometimes variables will drop out and you can change the magnitude of the initial variables if they change the problem. If instead of a 5 kilogram mass, they now want a 10 kilogram mass, not a problem. Just change it in this equation right here. And either way, you can quickly find new solutions, where if you put the numbers in at the beginning, you crank through a lot of math, you're doing a lot of math algebra, and that's not really as cool as just working with the letters. So here's our answer. Algebraically, we put in our numerical values, and let's just check the units here. We have kilograms on top, cancels here with the kilograms on the bottom. Here's our acceleration, meters per second squared, and the Atwood's machine will accelerate at 4.20 meters per second squared, which is less than gravitational acceleration. If block B was just dropped, it would accelerate at this, right? If you just had block B here and dropped it on the Earth, everything falls with the same acceleration. But why is it accelerating slower? Well, you have block A holding it back. Find the tension in the rope. Well, tension is the same for both masses, so we can use either the mass A equation over here on top or the mass B. We'll do both. Here you go for mass A. It's ma times A plus G. We put in our numbers. Here's our acceleration. Here's G. And we get 280 newtons. Now for block B, we have this equation. And you can see it's not a whole lot different. It's a little rearrangement and numbers are different. So in this case, either one would work. Neither one has any advantage over the other one. But in both cases, you get 280 newtons.